Section 4.4, the dimension of the vector space. So we have first theorem, let the vector space V has the basis B1, then any set in V containing more than n vectors must be linearly dependent. I think we've done this already. In other words, if a vector space has a basis B from B1 to Bn, then each linearly independent set in V has no more than n vectors. If the vector space V has a basis of n vectors, then every basis of V must contain of exactly n vectors. I think we've already discussed this. So now we have definition of the dimension of a vector space V is denoted by DIM-V. So if V is spanned by a finite set, then V is called finite dimensional. And the dimension is the number of vectors in the basis. Because the theorem before guarantees that each basis has the same number of vectors. So the number of vectors from the basis is the dimension of the vector space. But if V cannot be spanned by a finite set, then V is infinite dimensional. And by definition, dimension of the zero vector space is zero. This is just definition because zero vector is just one vector. We could have assumed it's one, but by definition, they set it up, it is zero. So now we have an example. We have example number 3 from the textbook. Find the basis of this set that is set of vectors like this and state the dimension. So we're gonna rewrite this vector using the A, B, and C. If I separate them, I have the spanning vectors. So this is the span. So the good candidates for basis are those 3 vectors as long as they are linearly independent. And on the side, we check the linear independence. So it turns out that indeed they are linearly independent. So the basis are those 3 vectors. If I have 3 vectors in the basis, that means the dimension is 3. The dimension of the vector space that is of this form. Example number 5 from the textbook. So find the basis and state the dimension. So we're gonna separate the vector using A, B, and C as we did before. And now we need to check if those 3 vectors are linearly independent, but we can notice that vector 3 is twice the vector 1. So that means they are scalar multiple of each other, so they are dependent. Removing one vector preserves the span. So the bases are nothing else but those 2 vectors. So if I have 2 vectors in the basis, that means the dimension is 2. If we have theorem, let H be a subspace of a finite dimensional vector space V, then any linearly independent set in H can be expanded if necessary to the basis of H. Also, H is finite dimensional and H dimension of the vector space of the subspace is no more than the dimension of the vector space. So the theorem basically says that the dimension of the subspace is always less than or equal to the dimension of the vector space. And then the basis theorem. So the basis theorem says if we know that V is p-dimensional vector space, then any linearly independent set of exactly p elements is automatically a basis. And also any set of exactly p elements that spans is automatically a basis of V. What that means, if you know the dimension of the vector space and you have the exact number of vectors as the dimension, it's enough to check on the one condition of the basis, either independence or the span. So the dimension of the null space is the number of free variable in the equation AX equal to 0. And of course, we've already talked about this before. And the dimension of the column is the number of pivots, is the number of pivot column of A. That's how the column space is found, right? So in other words, the free variables determine how many vectors we have in the null space, and the number of vectors determines the dimension. And pivot column determine the basis for column space, and how many vectors is there is the dimension of the column space. So now we have example. Now we have example that basis for null A and basis for find basis for null space and column space and find the dimension. And this example we've already done in class. So to find the basis for null space means nothing else but to solve the equation A times 0 vector is equal to 0 vector. Set up the matrix, put the 0 column, and solve the system. I encourage you to pause the video and solve the system until you get the solution. Once you have the solution, then we can form that those two vectors are linearly independent. You can check them, and they span because that's the span we have here. Set of all linear combination is the span. So the basis for null is nothing else but those two vectors. So the numbers of them is 2. That's determined by how many free variable you have. So the dimension of the null space is 2 because I have 2 vectors in the null, in the basis of null. And now to find the basis for column, we check the pivot column of the echelon form. Pivot column is first, second, and the fourth column. So we take we take the columns from the matrix for the basis. So basis for column are those vectors. And I have 3 vectors, so the dimension of column space is 3. Now we have example, find the dimension of the space spanned by the vectors, by 3 vectors. So if I have vector space that is spanned, so I'm looking nothing else as the same as column space. So to find, we need to identify the pivot columns by reducing the matrix to echelon form. So put the matrix and reduce it to echelon form. Perform row operations. Pause the video and try to do it on your own. Reduced form or reduced echelon form is this. So I can see that my pivots is first column and this second column. So for basis, we would take the first and second column of the original matrix or of the given, first and second. And because I have only 2 vectors in the basis, so the dimension of this vectors spanned, of the vector space spanned by the given vectors is 2. And the last example is 21 from the textbook. We have the first 4 Hermite polynomials are given this. Show that the first 4 Hermite polynomials form a basis for P3. So Hermite polynomials is name of those polynomials. So don't get too worried about what does that mean. So standard basis for vector space of polynomials of degree at most 3 is 1, t squared, or t cubed. Because out of those, you can create all the polynomials. Since the standard basis has 4 vectors in the basis, the dimension is 4. And since we have 4 Hermite vectors or polynomials, and each basis of P3 has 4 vectors, it is sufficient to show only that they are linearly independent. It's sufficient to show only one condition. So we need to check if this equation C1P1 plus C2P2 equal to 0 has only trivial solution. If we have only trivial solution, then the polynomials are linearly independent. So set up the equation and solve it. Set up the equation and solve it. So we have C1 times the first polynomial from the given, C2 times the second polynomial, C3 times the third, C4 times the fourth. Rearrange, multiply everything out, rearrange by setting together just numbers, coefficients standing with t, coefficient standing by t squared, coefficient standing by t cubed, and all of that is equal to 0, or in other words, 0 polynomial. 0 polynomial is 0 plus 0 times t plus 0 times t squared. 2 polynomials are equal if their coefficients are equal. So we're gonna compare the coefficient standing by t3, coefficient standing by t squared, coefficient standing by t, and then 0 polynomial. Once you solve it, you should get that all the coefficients turns out to be 0. And if I have 0, that means if the only solution is 0, that means the polynomials are linearly independent, and they form the basis.